These videos are offered on a pay-what-you-like basis. You can pay for the use of the videos at my website. There's a link to my website in the annotation. The address is www.freelance-teacher.com/videos.htm. Or you can just use the link in the annotation. Thank you. All right, well, we don't have too much more time left, but we'll start the next topic then here for section 5.3.
Okay.
Okay, so this section 5.3, it introduces a new notation that we haven't used before. So here's a new notation that we haven't used before, but this is going to be important for the rest of the course. This is what's called a definite integral. This is the notation for a definite integral. This symbol here then is an integral sign. This is the integral sign. Okay. What does this mean? This is easiest to explain with an example. This is this area. This definite integral is the area under the curve f between x equals 3 and x equals 6. That's what definite integral means. We might call that the graphical interpretation of an integral. What's the graphical interpretation of an integral? It's the area between the curve and the x-axis. What's the graphical interpretation of an integral? It's the area between the curve and the axis. Remember that earlier we talked about, so to put things in perspective, most of this course we've been studying derivatives. And I told you that derivatives are half of what the course is about. The other half is integrals. Half of the course is about derivatives and half is about integrals. We'll see very shortly that integrals are very closely related to antiderivatives. That's not really obvious right now, but integrals turn out to be closely related to antiderivatives. In any case, half of calculus is about derivatives and the other half is about integrals. Well, earlier we talked about the graphical interpretation of a derivative, right? Remember that the graphical interpretation of the derivative is the derivative tells you the slope of the tangent line to the function. Well, now we need to know the graphical interpretation of a definite integral. That's one of the main things your instructor is emphasizing in the problems for this section. Well, the graphical interpretation of the definite integral is that the definite integral tells you the area between the curve and the x-axis. The area between the function curve and the x-axis. So here would be an example of that. All right, so now what, for example, would this be? Well, that would be this. It would be this area, if you see what I'm saying. Okay. So these numbers here, these are called the limits of integration. That's just some terminology. The lower limit of integration here is 1, and the upper limit of integration here is 4. So those are our limits of integration. they tell you the 2 points on the x-axis that we're finding the area between. So how would you interpret this?
It's the area under the curve between 7 and 4.
Yeah, so it would be this area here.
Mm-hmm.
Good. What's this? What's the significance of this? Well, this just tells us the variable that we're taking the integral with respect to. So we could read this as, this is the definite integral of f of x with respect to x. The definite integral of f of x with respect to x. So it's kind of similar to the role that this played for the derivative notation. Basically, it tells us what the variable should be on our horizontal axis. This tells us what the variable should be on the horizontal axis. So if we changed, and this variable, so if we changed, say, to this, then we'd want to change the horizontal axis to t. This would be the integral with respect to t of f. The d of x, though, doesn't really have any separate meaning. Right now, you shouldn't really think that we're multiplying f times d. This doesn't have any separate meaning, just like this d of x, we hadn't really given that any separate meaning. We should just interpret it as telling us the variable that we're taking the integral with respect to.
Okay.
Now, what would this be? Well, this is a little bit different because when the obviously it's this area. However, when the curve is underneath the x-axis, the area is interpreted as a negative number. When the curve is underneath the x-axis, now this is interpreted as a negative number. For example, I don't know what this area really is, but it might be like -5 or -10 or -11. So that's another aspect of the definite integral. It's not just the area between the curve and the axis. When the curve is above the axis, the integral is a positive. It represents a positive area. But when the curve is below the axis, that's interpreted as a negative area.
Okay.
So how would you interpret this?
That's just, well, it's the area above the curve between 11 and 9.
Anything else to say about it?
It's going to be a negative number.
It'll be negative, yeah. So it's not just the area, it's the negative of the area, basically. It's the negative of the area here, because areas are always positive, right? Areas are always positive, but the definite integral would be the negative of that area. Okay, now this one is a little bit trickier. How would we calculate this? Well, clearly we're starting at 5 and going to 11. But now the curve is partly above the axis and partly below the axis. So what you do here then is, let's suppose that this area over here, let's suppose that that area, I'll just make up a number, but let's say that area turned out to be 20. And let's say that this area turned out to be 23.
Mm-hmm.
Then what would overall be the definite integral? Well, then the definite integral would be, so is this integral positive or negative? Is the integral positive or negative over this region?
Positive.
And is it positive or negative over this region?
It's negative.
The area is positive, but the integral is negative. So the integral here would be -3. So this is the first example we've done where there was a region both above and below the axis. So when there's a region both above and below the axis, you take the area, so where the curve is above the axis, you take the area, and where the curve is below the axis, you take the negative of the area, and then you add those together, and you get the overall definite integral. So what we're doing here is we're just defining the definite integral. Obviously, mathematicians can define weird symbols to mean whatever they like, and it turned out to be convenient to define this symbol to have these meanings that we're talking about. Okay, do you see how I got that -3 then?
Yeah.
All right.
So I'm guessing all the problems are set up like this, so you have one portion that's negative and one that's positive?
Not 100% of the problems, but yes, maybe because you're saying it would be too easy otherwise. So some of the problems are simple problems where the curve is just above or below the axis, but certainly on the test you can expect to see problems where it's partly above and partly below. Okay? Obviously, this is one of the two main concepts in calculus. The derivative is one concept and the integral is the other, so there's a lot more to this than we'll be getting to right now. There's so many ins and outs of this. We're just trying to start to sketch what this means. Okay, so how would we interpret or calculate this?
Let's see. 7. So it's the area. It's the negative area. It's between 12 and 8, and then the positive area between 8 and 7.
Now, I haven't put in any numbers here, but you can just eyeball this. Overall, is this going to come out to be a positive or a negative number?
A negative number.
How can you tell?
Because the area is negative is bigger than positive area.
Yeah, you can just see that this area here is way bigger than this area, assuming this was drawn to scale. For example, this number here might be 3, and I'm just making up brand new numbers here. But if I call that area 3 and I call this area 12, then what would be this definite integral?
That's 3, that's 12. Negative 9.
Okay, that's right. Okay, all right. So that's our first introduction then. So what section 5.3 does is introduces the definite integral. So that's our first introduction to how to think about the definite integral. And obviously we're going to have to go into much more detail about how to calculate the definite integral for various types of problems. Okay, how would you find the area of this shape?
The area of this shape is just 6 times 8.
Excellent. Good. Let's go ahead and calculate that.
Okay. 48.
Very good. Because the area of a rectangle is the base times the height. Very good. Mm-hmm. So try calculating the area of this shape.
Okay, that area is 1/2 the base times height, so 6 times 1.5. And that is 9.
Okay, good. So it's 1/2 3 times 6. Good. I think the way I would do this is like so. Would you agree this is legal?
Mm-hmm.
And what's 1/2 times 6?
3.
That way we don't need any decimals. Or you could also do it like this. What's 6 times 3?
18.
So you could also do it like this. Of course, if you're doing it in a calculator, it doesn't matter which way you're doing it. Okay, very good. So you remember that the area of a triangle is 1/2 the base times the height. By the way, I can't resist telling you why the area of a triangle is 1/2 the base times the height. What's the area of this whole rectangle?
Okay. The base times the height.
And obviously the triangle is half the rectangle, right?
Mm-hmm.
So if you agree that a rectangle is base times height, and you agree that a triangle is half of a rectangle, then we've just proven that the area of a triangle is 1/2 the base times the height. Okay, all right, very good.
Cool then. I never thought about it like that.
All right, and now let's take a look at this. Try working out this area.
Okay. So we can split that shape up into a triangle and a rectangle. And then the height of the triangle will be 2. And the base is still 3, so 1/2. That's 3 times 7. So 2. 1 second. So 10.5 for the triangle portion plus 5 times 3, so 15. So 25.5 for the whole shape.
Okay. So let's see. It sounds like your idea here was, since this is kind of a weird shape and we haven't learned how to find this area directly, it sounds like you had the idea of breaking this up into simpler shapes that you do know how to find. You broke it up into a triangle and a rectangle. That's good. That's not the only possible way to do this, but I think that's the best way, to break this up into a triangle and a rectangle for our purposes. But tell me again, how did you calculate the area of the triangle?
Okay, so the area of a triangle is 1/2 the base times height. So the base here is 3 because it has the same base as the rectangle side, 3. And the height is 7 minus 5, which is 2.
Did you draw that 2 into your picture?
Basically, yeah, but
Good. So you did something like this.
Mm-hmm.
Okay. All right, and then tell me how you calculated the area then of that triangle.
So now we take 2 times, yeah, I made a mistake. 2 times 1/2 times 3, which will be something different. Yeah, 2 times 1/2. Wait, 3 times 1/2. Well, I guess it doesn't matter. It's just 2 times 1/5 becomes 3. So the area of the triangle is 3 plus 15, so the area of the whole shape is 18.
Okay, yes. So your idea of how to solve this was a good one. Your idea was to split this up. That was a good one, but there was a mistake in our execution. I think you said this correctly. You said that this was a height of 2 and a base of 3, but then for some reason you didn't use those numbers when you actually did the calculation. I think you actually used the number 7. I think you went back and used the number 7. One thing that might help is to put a 3 here as well. So it's always good when you're doing geometry to write on your picture and write directly what all the key numbers are, because otherwise it's easy to make mistakes. Okay, so what was our area that we ended up with?
Total area of 18.
Okay, that's right. These are supposed to be straight lines and right angles.
Okay.
Okay, let's work out this area.
Okay. 10, 6. 2. 2. Okay, so the area of the triangle is 1/2 the base times the height. The base is 2, and the height is 4. We got 4 from 10 minus 6. That gives us the height of the triangle. So 4 times 1/2 2 is 4. So the area of the triangle is 4. And then the area of the rectangle is 6 times 2, which is 12. So total area is 16.
So again, the safest thing is to draw in that information that you figured out into your picture. And then that confirms, I think, that you did the right thing. 1/2 times 4. Okay, and what was your answer?
16.
Okay, very good. All right, so those are some high school geometry facts that we had to review. Very good. This is supposed to be a straight line. Okay. All right, so these are all supposed to be straight lines, although I wasn't very good at drawing them as straight lines. So here's our graph. Let's see. I'm going to label now the x-axis as t. Oh, so, no, that's not the x-axis anymore, is it? I'm going to label the horizontal axis as t. That will turn out to be convenient for this section of the chapter. And then I guess we can keep calling this y, I suppose. But this function now represents f. F of what? What's the input variable?
T.
That's right, not f of x, but here it's convenient to think of this as f of t. Okay, so now let's work out this. Okay. Oh, did you copy this onto your paper or onto your screen?
I started copying it, and then I figured that I wasn't supposed to because it was so extravagant.
Yeah. All right. So you'll have to work these problems out on paper and just kind of tell me what you're doing. Okay. So tell me how you would evaluate this.
Okay, so we're trying to find the integral of f of t. Well.
Oh, so actually that's not correct notation. We talked yesterday about here's the correct notation. So let me write it like this.
Okay, so we have to.
And now let's try that.
So we need to find the area above the t-axis and below. So, all right. I guess I'll start from the left. So on the left-hand side, I can break this up into different shapes. On the left hand, I'll make a triangle at t equals 4. And,
okay, now let's talk about that a little bit. I think you've forgotten to pay attention to these numbers. Do you remember what these numbers represent? These are called the limits of integration. What's the significance of these two numbers here?
We use them. Well, I know that we use, like we set t as t approaches 1, we find the limit, and then we subtract as t approaches 0.
Okay, that's actually not quite what I was going for here. I think you must be thinking of something else. So what this means is, so what does this mean? This means the area between f and the x-axis between 0 and 1. That would be this area. It sounds to me like you were trying to figure out how you would figure out the entire area. But these limits of integration tell you which area we're focusing on. This is something we talked about yesterday, but we haven't had too much time to practice this, so I think you might just have forgotten this from yesterday. So again, the key thing is we need to understand what these limits of integration mean. So this is the area under the between f and the x-axis, between f and the t-axis, between 0 and 1. Does that make sense?
The area between...
Well, it's this area right here. It's the area between f and the t-axis, between t equals 0 and t equals 1.
T equals 0. Okay.
So let's put that question aside because we need to understand those basic ideas first. So what would this mean?
The area between 2 and 6.
So it would be this area, right?
Yep.
Yeah, remember we did that exercise yesterday where I kept putting in the squiggles onto the graph to represent various areas and then undoing it? So that's what we're reviewing right here. So what would this represent?
The area between 10 and 13. So partially positive, partially negative.
Yeah, what would you do with the number that represents this area and the number that represents this area?
You subtract them from one another?
Right. Or probably that might be a little confusing. What you do is you make this a negative number and then you add them is the clearest thing to do. Okay, well then let's go back to the original question. How would you work this out?
Okay, the area between 0 and 1. So the height is 2, the base is 1. So the area is 1.
So that would be the area of that triangle, 1/2 the base times the height. Okay, that's right. So that definite integral. By the way, so how do you read this? This is the definite integral of f of t between 0 and 1. This is the definite integral of f of t between 0 and 1. How would you read this?
It's the definite integral of f of t between 0 and 1.
Good. And what's the graphical interpretation of a definite integral? Well, the graphical interpretation of a definite integral is it tells you the area between the curve and the axis. It tells you the area between the curve and the axis. So what's the area between the curve and the axis here? 1.
1.
Okay. Let's try this problem.
Okay. The definite integral of f of t between 2 and 0 is 4.
So the first thing you'd want to do is mark the area on your graph. You want to use an eraser so you can erase that. And then what was your answer?
4.
1/2 times 2 times 4. Looks good. Okay. Let's try this.
Okay, the definite integral of f of t between 0 and 5. So now we have to break up our shapes. So we can break up I guess we can take the area of the triangle from 0 to 3, and that would be 9. So the area of the triangle is 9. And then you add the area of the rectangle between 3 and 5, and that is 6 times 2, 12. So 12 plus 9 is 21. So the area of so the definite integral of f of t between 0 and 5 is 21.
So the first thing we do is mark in our picture that we're talking about this area here, and then we can break that up into the triangle and the rectangle. So it would be 1/2 the base times the height plus the base of the rectangle times the height. So that's 9 plus 12. Looks like we got that right. Okay, excellent. So we're seeing, what's the graphical interpretation of a definite integral?
It's the area that's under the curve.
Yeah, good. All right. By the way, what's the name of these numbers, 5 and 0? These are called the limits of integration. I think maybe that might have been what confused you into thinking we have to take limits here. So these are called the limits of integration, but they're totally different limits than the limits we talked about earlier. They're not this type of limit. They're just a totally different use of the word limits. They just mean the endpoints of integration, maybe instead of calling the limits. So I don't know what that was confusing us. But these are called the limits of integration, but they don't involve the concept of a limit directly. It's a different use of the word limits. Mm-hmm. Okay. Okay, so we did that correctly. Good. Let's see. I'll try this one.
Okay, the definite integral of f of t between 8 and 6. So we can break that shape into two shapes, a triangle and a rectangle. So the area of the rectangle is 6 times 2, which is 12. And the area of the triangle is 1/2 the base. So 1/2 of 2 is 1 times 2. So 1. So the area of the whole shape is 13.
Okay, so what's your answer?
13.
All right. Did you work that out on paper?
Yep. I like scratch work, but
okay. So we're doing this shape now.
6 times 2, the rectangle, which is 12. And the triangle is 1/2 of 2, which is 1, times the height. Okay, I made a mistake. The height is 2, so it's 1 times 2, which is 2. So the area of the whole shape is 14.
Okay, so it's always good to double check our steps here. I don't know if you know what went wrong the first time. Maybe you did, well, I don't know. But anyway, the best thing is to actually draw out the shape and write out all of the calculations that we're doing, because otherwise it would be easy to make a careless mistake on that. But conceptually, that was the right approach, using the splitting this shape up into a rectangle and a triangle. Let's try this one.
Okay. Okay, the area between 8 and 9. So the rectangle is 6 times 1, so the area of the rectangle is 6. And the area of the triangle is 1. So the total area of the shape is 7. So the definite integral of f of t between 9 and 8 is 7.
So now we're talking about this area. So base times the height of the rectangle plus 1/2 the base times the height, 6 plus 1. Okay, looks like we got that one correct. Very good. Can you read what I wrote here?
Yep.
Okay.
15, 13.
So let's try this one.
15 and 13. Okay. So between 13 and 15, well, we can let's see. Okay, so we can split the area between 13 and 15 up into two shapes, a rectangle and a triangle, and the rectangle is 2 times 2.
One moment. Let me think about this for a second. Sorry. This didn't make sense. Okay, so this point here should really be at -6, not -5, in order for this to make sense. Sorry about that. So we can fix that on our picture. And then let's start again and give that another shot.
Okay. So we can split it up. The rectangle, the area of the rectangle is 4, which is really -4. So the area of the rectangle is -4. And then the area of the triangle is 1/2 of 2 times 4. So the area of the triangle is 4. So the area, the definite integral of f of t between 15 and 13 is -8.
Okay, so now we're talking about this area. Good. Good. Excellent. So you did that correctly. Here's how I would write that. I would just put a negative sign out here in front of the parentheses, and then we could say the rectangle has a base of 2 and a height of 2, and the triangle has a base of 2 and a height of 4. And then what was your answer?
-8.
Good. So I think this is the best way to write that out. Areas are always positive. Areas are positive. Lengths and widths and heights are always positive. So these are all positive numbers, but we have to stick a negative out in front to show that in definite integral land, this represents a negative result. All right, now you must have done something like that. Okay, so you ended up with the right answer there. Okay, that's good. I'm going to erase some of the ones we did before to make some room, but it would be good to have those in your notes so you could go back and try them again, or you could rewatch the video to try them again. This is a type of question that's definitely going to be on the test, so we want to make sure we'll get full credit on it. They're not super hard once you get the hang of it, so we just want to make sure we understand all the little details. Let's see.
Okay, between 9 and 13.
Good, yes.
Okay, so we have a positive triangle between 9 and 12. And the area is positive between 9 and 12, so that's 1, 2. So 4, 1/2 of 4 times 6. So the area of the triangle is 12 plus.
Let's back up for a second. Let's see. Where did you get that number 4 from?
Okay, yeah, that's wrong. Should be 3. So the area of the triangle is 9.
Okie dokie.
Okay. And the area of the other triangle is 1 times 2. So the area of that triangle is 1. So we have 9 minus 1. So the definite integral of f of t between 13 and 9 is 8.
Okay, good. So I would write that out like this. One of our areas is 1/2 times the base, which is 3, times the height, which is 6. And now we're going to subtract the other area because it's in the negative region. So that would be 1/2 times 1 times 2. All right, and then you could do this by hand or on your calculator, and you would end up with, what was your answer?
8.
Positive or negative?
Positive.
Why could we see from the start the answer was going to come out positive?
Because the area of the triangle that's above the t-axis is bigger than the area of the triangle that's below the t-axis.
Yeah, we can clearly see from the start that this triangle is going to be bigger than this one. So we could eyeball it and see this number would be bigger. Okay, so the one issue that messed us up here was a careless mistake with one of the lengths. This number here, at first you were putting in a 4. How do we come up with this 3? How do you get that number 3?
12 minus 9.
That's right. Or, if you wanted to, you could just say 1, 2, 3. I mean, you don't even have to do subtraction. You can just count 1, 2, 3 to see that that's going to be the width there. Okay, good. All right, good. That's the correct way to do that. Let's look at this then. Let's try this one.
Okay. 20 and 15. Okay, so the area of the triangle between 18 and 20 is 4. So we have 4 minus let's see. Three minus 18, which is negative 15. So the definite integral of f of t between 20 and 15 is negative 15.
Okay, let's see. So did you diagram out on your picture which 2 areas you're looking at?
I just wrote down the numbers.
Okay, it's always safest to try to indicate, I guess this is a little bit, it's easier on the screen than on paper because it's easier to erase, I guess. But if you do it lightly, it's always good to actually try to write things down on paper because otherwise people tend to make mistakes. Okay, talk me through that again then. What was your process?
Okay, so we're looking at the area between 15 and 20. So
Good.
I'm looking at the triangle to the right of 18.
Okay.
And the base of that triangle is 2.
Mm-hmm.
And the height is 4. So 1/2 of 2 is 1. 1 times 4 is 4. So now we have positive 4
Okay, that sounds good. Okay, that's fair enough. All right, what else?
And then now we're going to subtract the area of the triangle between 15 and 18, and that is going to be 1/2 of 3 times 6. So 1/2 of 6 is 3 times 3 is 9. And then 4 minus 9 is -5.
Okay. Oh, I didn't think that was the first answer you gave. Was that what you said? Was that what you had written down as your answer before?
No, I had -15.
All right, something must have gone wrong. Can you see what went wrong the first time?
I think I just wrote down, my math's the same. I just wrote down a 1. I don't know.
Okay. All right. So it's just important to take our time on this and make sure we want to make sure we can get these right without, not just that we know how to get them right, but that we can get them right without careless mistakes. So we might as well demonstrate that now during the tutoring so that we've got that demonstrated by for when the test comes up. Okay. So what's your answer?
-5.
All right. So I would write that out like this. So first I would do this area. I put a negative sign in front because that area is negative, and that would be 1/2, and then the base is 3, and the height is 6. And then the next area is positive, 1/2 times the base times the height. And then you could just do this in one step on your calculator. You could just type this in on your calculator now, or you could do it step by step if you like. So that's 4 minus 9. So what was the answer?
Answer is -5.
That's right. Okay, good. And we can kind of see that because this triangle looks bigger than this triangle. Or I don't know if it really does, but if I drew this to scale, it would have looked bigger. Okay.
Mm-hmm.
Okay, let's try this.
Okay. The area between 19 and 16. So a small triangle to the right of 18 is the area is 1. So 1 minus the area of the triangle to the left of 18, which is 1/2 of 2 times 6. So 6. So the area of everything is 1 minus 6, which is -5. That can't be right. You just got -5 for the other answer. 1/2, 2. It's 1 times 1. So 1 minus 1, 2, 3, 16, 1, 2, 2, 1/2 of 2, which is 1 times 6. Oh, no, it doesn't go down to 6. It goes down to 4. So 1 minus 4, so the area is -3.
Well, I think maybe you're confusing yourself now. So let's see, which triangle's area are you figuring out?
The triangle to the left of 18.
Okay, and what's the height of that triangle?
4.
Let's see. No, I was confusing myself. You were clear, I was confused. Okay, actually you're right. You're right about that. Good.
Okay. So if the area of that triangle is 4, we have 1 minus 4 equals -3. So the definite integral of f of t between 19 and 16 is -3.
Okay, well, let's see. So so again, it's good to indicate that we're doing this area here from here to here. So the first triangle has a negative area, so it's 1/2, and the base is 2. And you're right, the height is 4. It's a little unclear because my picture was such a mess, but you deciphered it. The height is 4. You were right about that. All right, and then this triangle has the positive area, and its base is 1, and its height is 2. So then we had -4 plus 1, and what was your answer?
-3.
Okay, good. Looks like you got that correct. Okay, very good. I think I was going to make a mistake on that one too. I thought our first answer was correct, but you felt that something seemed a little bit weird about that since it was the same as the previous answer. It's not impossible for two definite integrals to be the same, but in this case, it felt like that was weird to you, and your instincts were correct. That actually turned out to be wrong. I made that same mistake of putting in the 6 and not the 4. So it looks like you got that correct. Okay, good. All right. Okay, let's see. Okay, good. Well, you can practice more of these on your own, but I think now we're getting the basic idea of those problems. It's good to practice them some more so we can get to the point where we don't make some careless mistakes, but conceptually we're understanding that. So let's move on now to the next topic. I think I'm going to erase all of these so I can write more on here, but it would be good to go back and do those problems again later. They'll all be saved in the video. Now, so how is this read aloud?
The definite integral of f of t between 6 and 4.
Good. Although I think it would be more natural to say between 4 and 6.
Between 4 and
You're
6.
probably saying 6 and 4 because your eye hit the number 6 first, but 4 comes first on the number line, so it'd probably be better to say between 4 and 6. Good. Now, what's the graphical interpretation of this definite integral?
It's the area that's under the curve or
Good.
above the curve.
Yeah, area between the curve and the axis. It's the area between the curve and the axis, roughly speaking. Okay, now remember that the two main subjects in calculus are derivatives and integrals. Two main subjects are derivatives and integrals. We've already seen the graphical interpretation of derivatives, right? Remember that the derivative of a function, the graphical interpretation of that is it gives you the slope of the tangent line to the function. And now we've seen the graphical interpretation of definite integrals. The graphical interpretation of a definite integral of f is it tells you the area between f and the axis. This is the area between f and the axis. Whoops. Now I'm going to write down a kind of weird looking function. So we'll have to kind of digest and meditate on this weird looking function. What's weird about this? The weird thing is now there's a variable as the limit of integration. Before we had numbers up here, but now I have a variable as this limit of integration. By the way, you can kind of see now why we had to call this the t-axis, because we were saving x for something else. This is the t-axis because we're saving x for something else. So what is the input to g?
The input to G is X.
Not T. Notice, not T. X is the input to G, not T. Now, what the heck does this mean? Well, let's try to work that out. What would this mean? Well, what should I write here?
1.
Okay, very good. And what does this mean?
The definite integral of f of t between 0 and 1.
Good. And what's its graphical interpretation? That's what I want to focus on more. What's the graphical meaning of this?
It's the area between the axis and the curve.
Between 0 and 1.
Yeah.
Good. So it's this area.
Mm-hmm.
So this area here is g of 1. This area here is g of 1. So what's g of 2?
The area between 0 and 2.
So g of 2 would be this area.
Mm-hmm.
So what we're trying to do is get a feel for what this g function means and what it means for the variable to be a limit of integration. So what's g of 3?
The area between 0 and 3. So that whole triangle.
So this would be g of 3. Okay, good. So your textbook has a good name for this g function. Your textbook calls the g function the area so far function. Why do they call it that?
Because it's only the area at certain points. So, I'm not sure how to word it. It's the area under the curve, but only in certain intervals. Like, for example, like we use 0 and 2. That's only the area under the curve between 0 and 2.
So, for example, does this tell you the entire area from 0 to 20?
No.
No. It just says, so g is basically an area function. So you can imagine someone who's imagine like a little person walking along the axis. So when the person gets this far, they say, well, so far I've passed an area of g1. And then let's say the person walks further and they get to 2. Well, then they could say, now so far I've passed an area of g of 2. The area so far is g of 2. By the time they get here to 6, they can say, well, the area I've passed so far between 0 and 6 is g of 6. So this doesn't tell us the total area under the curve. It tells you the area so far if you started walking at 0 and you got to 1 or 2 or 3 or 4. So I think that hopefully that makes sense. I think that's a very good way of describing this that the textbook uses. It's the area so far function. I think that's a good thing to keep in mind. That should help to keep us understanding. We really need to kind of understand what this function means. So it's the area so far function. Okay. It's important here not to confuse then x and t. So this is the t-axis, and then g is defined as a function of x. X tells us how far we've moved from 0 along the t-axis. X tells us how far we've moved from 0 along the t-axis. Mm-hmm. So what's the input to g, x or t?
X.
Yeah, x, not t. Okay. Okay, good. By the way, something we haven't talked about that maybe we should have. What on earth could this mean? What is this?
That means just a point.
So
we're not looking.
This would be, or maybe I should actually do this instead. So this would be the area. It would be this area here, right?
Mm-hmm.
But what is the area of this line?
0.
Yes, because its width is 6. Its height is 6. But what's the width of a line?
0.
Yeah. So the area under a line is always 0. So this integral, this definite integral is 0. So what's this?
0.
Yeah. Anytime the two limits of integration are the same, the definite integral has to be 0. Because then you're just finding the area under a point. Well, the area under a point has to be 0 because there's 0 width. So that's a little fact that I should have mentioned before.
Okay.
So what's this?
0.
Because we just said whenever the two limits are the same, the area has to be 0. So what's this?
Which one? Oh, g of 0. Oh, 0.
Because what does g of 0 mean? It means the integral from 0 to
0.
And what is that integral?
0.
As we were just talking about, anytime the two limits are the same. Okay, so let's say you have the little person that starts here at 0. So what's their g at this point?
G at 0?
Yeah.
Their area is 0.
Because how much area have they passed so far? None. They haven't started moving yet. Now let's say they move from here to here. would that increase or decrease g?
Increase.
Good. Now let's say they move from 1 to 2. Would that increase or decrease g?
Increase.
Because g of 2 is bigger than g of 1, because they've added more area. How'd say they move to here? Does that increase or decrease g?
Increase.
Because that adds this chunk of area. When they move here, does that increase or decrease g?
Increase.
Because that adds this chunk of area. Increase or decrease when they move to here?
Increase.
Does g increase or decrease when they go to here?
Increase.
All right. Well, let's say they're here, and let's say they move to 9. Does that increase or decrease g?
8 to 9. Let's see. Well, area is cumulative, so it increases.
Okay, good. That's a good answer. I was trying to trick you. I think some people might say here, well, gee, f is decreasing. But who cares about f? I was asking you about g, right? So it's important not to confuse f and g. Would you agree that f is decreasing from 8 to 9?
Yeah.
But who cares? I was asking about g. Is g increasing or decreasing from 8 to 9?
Increasing.
Okay, so it's very important now. We have two functions in this problem, and it's very important not to confuse them. You didn't confuse them, but I'm just warning you to continue not confusing them. We don't want to confuse g and f. Even though f is decreasing here, g is still increasing. How much did it increase by? It increased by this chunk of area when we went from 8 to 9. Okay, so let's say I go from 9 to 10. Does g increase or decrease?
Increases.
By this chunk of area. Let's say we go from 10 to 11. Does g increase or decrease?
Increases.
By this chunk of area. Now if we go from 11 to 12, does g increase or decrease?
Increases.
It still increases. Even though f is 0, g is still increasing by this little area. Now let's say we go from 12 to 13. Did g increase or decrease?
Decrease.
All right, finally we got a decrease. Good. All right, how much did it decrease by?
By the area between 12 and 13.
By this little triangle, right?
Right.
In fact, you could quickly calculate it. It's 1/2 times 1 times 2, so it would decrease by 1 unit.
Mm-hmm.
Okay, so now we've finally seen what it looks like when g is decreasing. Now let's say we move to here. Does g increase or decrease?
Decrease.
It decreased by now this trapezoid.
Mm-hmm.
Let's say we move from 14 to 15. Did g increase or decrease?
Decreased further.
Good. How about when we move from 15 to 16?
Decreased further.
Even though f was increasing.
Mm-hmm.
Yeah, because f is not the same thing as g. F was increasing here, but g decreased. How much did g decrease by? Well, by this amount. Because we'd have to take the previous g and subtract this area to find the new g. We'd have to take the previous g and subtract that area to find the new g, to find the area so far. Good. Now how about when we move to 17? Does g increase or decrease?
Still decrease.
Good. How about 17 to 18?
Still decreasing.
Although only by a small amount. Good.
Mm-hmm.
How about when we move from 18 to 19? What happens to g?
Starts increasing.
It increases again by this amount. Good. And then what happens when we move from 19 to 20?
Also increasing still.
Okay, so this is a type of question that's pretty sure to be on the test. I'd like asking, where is this weird g function increasing or decreasing? Remember, another name for the g function is the area so far function. So we need to be able to tell where g is increasing or decreasing. So how would you summarize it here? What was the intervals where g was increasing, and what were the intervals where g was decreasing?
Let's see. G is increasing on 0 to 12 and 18 to 20. And then G is decreasing on 12 to 18.
Okay. So the main thing you have to watch out for here is don't start answering where f is increasing or decreasing. F is totally different. Where f is increasing and decreasing would be totally different answers, but we were focusing on where g. So notice, does this graph show g directly? Maybe kind of a weird question, but for example, here this point is 4. Does that number 4 tell you g directly? Is g of 2 equal to 4?
No.
No. Is this curve a graph of G?
It's not.
No, it's a graph of F. Now, it's kind of a weird question because you can figure out G from the picture. You can figure out G from the picture, but it's not really, the curve is not a picture of G. That's the thing you have to keep in mind. Okay. Okay, so this is a type of question that you're very likely to be tested on, and it looks like we worked it out. How would you summarize this then? In general, how do you know when G is increasing and when G is decreasing? What do 0, 12, and 18, 20 have in common with each other?
Those points are where the function f is positive, and when f's negative, then G is decreasing.
Excellent. Good. So it looks like we've come up with a, well, we just did a little math here. We just came up with a theorem. We came up with the theorem that when f is positive, what does that tell you?
G is increasing.
And when f is negative, what does that tell you?
G is decreasing.
Excellent. And if you forgot that, you could kind of figure it out. If you remember that G is the area so far function, you can figure out why these things make sense. Okay, good. Maybe this should really be called the f-axis. Okay, because we're not really using y. Now, remember that we've said that the area so far function is usually symbolized here with a g. And what symbol do we usually use as the input for the area so far function?
X.
Even though there's no x's yet on that graph. What would I write here then to define the area so far function?
The area so far function, g of x equals the limits of integration of x to 0 of f of t with respect to t.
Okay, good. Excellent. That's very good. A slightly better way to say that is this is the integral from 0 to x of f of t. But you are obviously thinking of the right thing. This is the integral from 0 to x of f of t. But you were definitely thinking of the right thing. So it's kind of a weird, complicated function, but I think we've been making some good progress on understanding this function. So these are all hash marks of 1.
Mm-hmm. Okay.
All hash marks of 1. Okay, so
okay. So g of x is increasing from 0 to 5, and also at 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. So g of x is increasing from 0 to 5 and from 18 to 19, 20, 21, 22, 23, 18 to 23. And then g of x is decreasing from 5, 6, 7, 8, 9, 10, 12, 13, 14, 16, 17, 5 to 18. I was just counting again to make sure I was counting right the first time. Yep, so 5 to 18.
That was a smart way to double check. Good. Okay. Let's see. 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Perfect. Okay, very good. So that's one of the types of problems you're likely pretty sure to see on the test. So let's label this a little bit then. We could say that this is the region where G is decreasing. And what can we say about this region?
Wait.
Oops. What should I say about this region?
Increase.
Thanks. Okay. Good. How about here?
The area where G is decreasing.
And here?
G is increasing.
Although actually maybe we did that out of order. Maybe first we should have said this is the region where F is positive. That's how we determined that G was increasing. And what could we see first about this region?
F's negative.
So it's contributing negative area to the area so far function, which pulls the area so far function down, which makes G decrease. Good. By the way, does G have to be negative in this area, in this region?
Let's see. No.
No, it just has to be decreasing. This is something we were talking about earlier. Negative doesn't mean decreasing. Positive doesn't mean increasing. So we don't want to confuse these with each other. These are two separate things. For example, at this point, is G positive or negative? At this point, would G be positive or negative?
G is positive.
Because it represents this area.
Mm-hmm.
And then how about, say, at this point, is G positive or negative?
G is still positive.
Yeah, even though it just decreased by a tiny amount. It just decreased by this tiny amount, but that's not enough to outweigh all the big area that it already had accumulated. So there's a big difference between decreasing and being negative. I think probably G would eventually get negative, because this is a pretty long region here, but it doesn't have to be negative over the whole region. And then here, what's the first thing we could figure out about this region?
That F is positive.
So what does that tell us about G?
G is increasing.
Does that mean F is increasing?
No.
No, you can see there's clearly a part where F is decreasing. So it only tells us what it tells us. We can't confuse what we know about F with what we know about G. Those are two different things. This is similar to some ideas we talked about earlier. Okay, so if G is increasing on this interval and G is decreasing on this interval, what can you tell me about G at this point?
That's our...
Let's say we drew a graph of G. We haven't drawn a graph of G. Is this a graph of G?
Nope.
No, but I could draw a graph of G. If I did draw a graph of G, what would be happening to that graph at this point?
Let's see. That's going to be where the derivative of G is 0.
That's true. What does that mean about its graph?
The slope is 0.
Good. Let's use this information a little bit more.
Okay.
In this region, G is increasing. And in this region, G is decreasing. So what does that tell us about the graph at this point of G?
There's a local max.
Yeah, that's right.
Okay.
A local max of who?
The local max of G.
Not of F.
Mm-hmm.
Okay, does that make sense? If you're increasing up to this point and then you're decreasing away from that point, you must be at a max at that point. So the graph of G must look something like this at this point, increasing up to the point and decreasing away from the point. Good. Well, G was decreasing on this region and increasing on this region. So what can we say about G at this point?
There's a local min at that point of G. Local min of G at that point.
That's right, because if you're decreasing and then you start increasing, you must have a minimum. Good. Okay. Well, these are two more things that you're likely to be tested on. We can use F to figure information out about G. we can use f to figure information out about g, even though this is not a graph of g directly. And this should remind you of some stuff we went over in the previous chapter. It's kind of a similar thought process. So all these little notations I'm making here, these are the notations I would encourage you to make. Actually label the regions where f is positive, label a negative, label where g is increasing or decreasing, label the local mins and maxes right on the graph, just like we did in the previous chapter. All those same notational tricks we used before can still serve us well here. Let's go back to the previous question that we've been doing then.
Okay.
So on this problem,
Okay. Let's see. Well, g is increasing from, well, first we'd say f is positive from 0 to 12, which means g is increasing from 0 to 12. And then f is negative from 12 to 18, so that means g is decreasing from 12 to 18. So when t equals 12, we have a local max. And then we have...
One moment. So the local max occurs where?
At 12.
When who's equal to 12?
When g is 12, g of 12.
So what would be the input that makes... So what's the input for g?
12.
Yeah, what variable has to equal 12?
X.
Not t.
Right.
What's the name of the variable that's the input for g?
X.
Good. So there was a slight mistake in what you said before, because you had said that local max was where t equals 12. But t is the input for the f function. T is the input for the f function. What's the input for the g function?
X.
And what's the input for the f function?
T.
That's right. Okay, so is this question asking us for a g, for an x, or a t?
An x value.
Okay, good. We saw in that last test that the graders can sometimes be pretty picky, so that's a good thing to be careful about. Okay, so your logic was correct, but this max occurs where x is equal to 12. Okay, and that's a max of who?
G.
Okay, very good. All right, good. You're doing good. What else?
Okay. So now we have a local min at, let's see, g is decreasing till 18 and then increasing after 18. So we have a local min at x equals 18.
A min of what?
G, local min.
We should probably say that because it's not a minimum of f. We have two different functions here, so we have to be careful. Good. And what's the first thing we figure out about this region? How do we know that g is increasing on this region?
Because the function f is positive in that region.
That's right. So that would be a good thing to write down. So again, if this was a test question, it would be best to write out this whole type of all these labels like we have done on previous sections. Okay, so it looks like you got that correct. Good. What's our normal input for our g function here?
X.
And how would I write the g function in this case?
How would you write the g function? The g function in this case is g of x equals the integral of 0 to 1, 2, 3, 4, 5, 6. 0 to 6 of f of t with respect to t.
Okay, that turned out not to be quite right, because what's the input for the g function?
The input for the g function is x.
But notice there's no x's here, so we must have made a mistake.
Okay. Of 0 to x.
That's right. Remember, that's what makes this a weird function. What makes it weird is that we're putting in a variable for the limit of integration. But remember, it shouldn't be too weird anymore, because I think we've worked on understanding what this means. This is why this is called the area so far function, right? Remember, what's the graphical interpretation of an integral? The graphical interpretation of an integral is the integral tells you the area. But if this limit is a variable, then it tells you the area so far. So that's very important to put in this x here. This is the area so far function. Okay?
Okay. So
Let's try this on your screen.
Okay. So the question was where g is increasing. One, two.
Let's try to do the whole thing without scrolling so we can see the graph at the same time as we're doing our answer.
Okay.
Okay, can you read that last sentence that you just wrote? G has a local, what does that say?
Max
And the rest of the sentence?
of x equals 4.
Okay, that's not quite right. In fact, that's something that was the thing that we had trouble with on that last test. The max is at x equals 4. we don't actually know what the local max is, right? Because I didn't label the y-axis here. So it has a local max of something that's unknown. We don't know what the local max is because I didn't label the f-axis. So we should fix the previous sentence too. Okay, good. Okay, good. So I guess on these problems, we're actually kind of using the horizontal axis to stand for two different variables. We could call it the t and the x-axis. We're kind of using the horizontal axis. It stands for t for the f function and x for the g function. Let's not label it as x because that's not what your instructor does. They just label it as t. But in our mind, we should know that it kind of stands for x as well. Kind of, sort of. Okay. All right, very good. All right, good. All right, well, I was making a minor criticism of the wording there, but that was correct. That was a good process. So that's the right way to do that. Good. Okay, good. I'll go back to my screen. So which of these two questions should we logically answer first?
Where g is increasing or decreasing.
Even though I asked it second, right? That was one of the things that you did that was a good idea on that problem. Even though I asked you this first, you didn't get bamboozled by that, you still answered this question first. In fact, notice, even if they hadn't asked us this, we still have to know this to figure out this, right? Even if they don't ask you where g is increasing or decreasing, you still have to figure it out so you can figure out where the local maximums and minimums are, okay? So what you did here is you split this up into intervals. You said this is the interval where f is positive, so g is increasing. And here we had f negative, so g decreasing. And here's where f is positive, so g is increasing. Something we could have done, we could have said, what do you know about f here?
F is 0.
That's true. And what do you know about g there?
Let's see, g has a local min.
Okay, and then at this point, what could you say about f?
F equals 0, and g has a local max.
A little hard to fit it in here, but that's right. Okay, good. So notice the points where f equals 0, those seem to be the candidates for where g has a local min or max. The points where f equals 0, those seem to be the candidates for where g has a local min or max. They don't guarantee that g has a local min or max, because after all, f was 0 here. But this is not a local minimum or maximum using the definition in your textbook, because remember your textbook definition says you can't have a local min or max in the endpoint. And f was 0 here, but there wasn't a local min or max here either, according to your textbook's definition. So where f equals 0, those are the candidates for where g can have a local minimum or maximum. I'm not saying you have to write this down necessarily, although it couldn't hurt to write that down. But those help give us the candidates for where g is a local min or max. And then how do we know this is really a local min? Well, because we saw that g was increasing up to it and decreasing away from it. So that proves it's a local min. And since g was decreasing down to here and increasing from here, that proved there was a local max there. Okay, good. Okay, so again, g, remember, is what we call the area so far function. What do we usually use as the input for that? What symbol?
X.
And then how would I write the formula then for g in this case?
The integral of 0 to x of f of t with respect to t.
Perfect. Okay, good. Okay, so try this problem.
this is just from 0 to 3, so 3, 6, 9. The definite integral of f of t from 0 to 3 is nine.
So what's the answer?
9.
Okay, excellent. All right, and from what you were saying, it sounded like you used a very good approach. It sounds like the first thing you did is you used this definition we were just talking about. And what do we plug in here?
3.
Good. That was the key. Excellent. So you did that correctly. And then this type of problem we already know how to do, right? Didn't we? We spent, I don't know, half an hour or more doing those types of problems earlier on, right? We did a whole bunch of those different types of problems. We already know how to do that. Because what's the graphical interpretation of a definite integral?
It's the area between the x or t or whatever axis you want to call it and the slope of the function.
Let's see. It's
the
the area between the axis and the function. We haven't really been talking about slope exactly. It's the area between the axis and the function. Good. Between the limits of integration. I guess it's a little bit complicated to describe the whole thing, but the point is that it's the areas we've been talking about. Good. And then you figured out it was again an area of a triangle. 1/2 the base times the height. And what was your answer?
9.
Perfect. Excellent. And what's this?
I think that's the same question.
So what's the answer?
9.
Good. Well, why did I just answer the same question twice? Well, because there were two different questions. My point is, do you agree these are both the same question?
Yeah.
Yeah. Okay, so that's the main point I was making. These are two ways of asking the same question. Two ways of asking the same question. So earlier on, we did a whole bunch of questions that look like this. But we could just as well have been writing them all like this. It's the same question either way, is my point. And you really figured that out for yourself here because you rewrote this in terms of the definite integral notation, and you saw for yourself it's really the same type of question we were doing earlier. Let me point out again a mistake that you did not make, but that we might fall into eventually. So here you had, what was the input to this function?
3.
What did we plug the 3 in for?
X.
X or t?
X.
Good. So the mistake that I think a person might easily make would be to write this. Do you see this would be wrong?
Mm-hmm.
Yeah. So we have to be very careful here. Remember, t is the input for f, but x is the input for g. You didn't make that mistake, but maybe we might want to inoculate ourselves against it anyway. So what we had here is we have a function with two variables. You have to know where to plug in this 3. Well, we're not plugging the 3 in for the t. We're plugging in for the x. You did that correctly. Okay, good. All right, let's see. Well, anyway, here's the problem.
Okay. So find all of this.
Yeah, and maybe we'll do this on your screen. So take your time and try copying this back onto your screen. So this graph is not as complicated as the one before. So if you take your time, it shouldn't be too hard to copy it exactly onto your screen, and then we can do it on your screen.
All right. So Okay. So we have 1 times 2 plus 1/2 times 2 times 1 plus so that means 6.
Okay, let's see. I think we might have made a mistake on that problem. We've made some careless mistakes on some of these problems. I think the way to avoid that is to build more information into the picture. So let's see, your 1 times 2, point to the shape that that 1 times 2 represents.
Right here.
So the long rectangle?
Yep.
Okay, good. And then you have 1/2 times 2 times 1. Point to the shape that that represents.
This triangle.
Okay, good. So what's the height of that triangle?
1.
And what's the width?
1.
How could we avoid that? I think the problem here is that the height is not directly in the picture. So when you're doing that problem, it probably would be a good idea to actually label the height in your picture, if you see what I'm saying, with the hash marks like we did before. It's better to have all the things labeled out ahead of time before you start writing the formulas, because I think we've seen that it's easy to make careless mistakes on these otherwise. So label the height of 1.
I'm not sure.
So what distance does that represent? Just show which distance represents the height and label that as 1.
Height.
Good. But what I'm saying is we should label that with the number 1 before we start writing the formula. Because we put down the wrong number, right? We put down the number 2 because we didn't have the right number in our picture. So let's actually label what's the distance. Let's label that height with a 1. Good. Okay, so that's the best approach here to make sure that we're avoiding mistakes on those types of problems. Okay, good. So I guess we'll have to go back and try that one again.
All right. Okay. Is that one right?
I think I'll let you keep working and you can decide for yourself whether your answers are right.
Okay.
I think you might have miscopied this problem.
I don't think so.
Let's see. What was so your integral is from where to where?
6 to 8.
Oh, okay. It doesn't look like you wrote down a 6.
Okay. Oh, shucks. All right.
Okay. Well, actually, we are making some mistakes here. The problem here is that we've forgotten that when the area is underneath the t-axis, it represents a negative number.
Okay.
Well, let's just read. Oh, let's see. Maybe I'm the one that's confused. 6 to 8. No. Okay. So I guess we're having some trouble here. So let's not. Let's try to make the alterations we need. Okay, that looks better.
That's right. I'm just going to redo all these. I did them all wrong. All right. 0 to 3. Okay. I think that's the same answer I got, so I'm not sure.
Yeah. Well, our answer for A was incorrect the first time just because we put in an incorrect height. Remember, we used a height of 2 rather than 1. But after we fixed that, there was no reason to think that that work was incorrect.
Okay. All right. So
right, so here's where we're having trouble. Again, I think we might have started to forget. Remember, the areas that represent the areas when the curve is underneath the t-axis have to be treated as negative. That was what was giving us trouble. So let's erase that last line. And fix your first line. That first line is not quite right because we're not taking into account that the areas above, the areas below the axis represent negative numbers. Yeah, let's go ahead and, okay, fair enough, good. You could just say minus instead of plus or minus.
Okay.
But maybe this is just the best, this is for the best. Check your arithmetic on the last problem. Okay, and you can always just do that on the calculator. In fact, you could have done that first expression on the calculator. Negative 1/2 times 1 times 1 plus negative 1 times 1 minus 1 times 1 minus 1/2 times 1 times 1. The calculator could do that in one step too. But it's always, people just have a real hard time doing arithmetic without making mistakes, so it's always important to double check those steps. Okay, good.
Okay.
Okay, good. So the thing that was giving us trouble with this before is we were forgetting to represent some of the areas as negatives. But remember, that was the whole point. Remember, we've seen that when f is positive, the area so far function is increasing. But remember, we've seen that when f is below the t-axis, the area so far function is decreasing. Why would the area, how could the area so far ever decrease? Remember, we've seen that sometimes the area so far increases, but sometimes the area so far decreases. How could the area so far ever decrease? Well, the only reason it can decrease is because we're treating some of the areas as negative. So that's a very important part of the definition of the definite integral. It represents areas, but some of the areas are treated as negative. Otherwise, that g function could never have a region where it was decreasing. Okay, so I think we're getting those right now. Good, so we can try D.
Okay.
Let's see.
I just
took the pieces. In this problem, the pieces almost add up to 0 to 8. So 3, -3, and then you have to add one other part.
Okay, that was a good way to do that. That's a good insight into the intuition here. So what you saw is that definite integrals can be broken up into pieces and then added together. You just kind of proved a theorem or figured out a theorem about definite integrals. That's very good. So that shows we have some good intuition for this here. So yeah, from 0 to 3 was 3. From 3 to 7 was -3. So those canceled, and all was left was from 7 to 8, which was 1/2. Okay, excellent. Good. Okay, so this would be good to go back and practice again because we want to make sure we can do this without careless mistakes. We saw the importance of the negative areas. Well, let's continue with part E for that same problem.
Okay.
So you can copy that down and then try part E on your screen. Let's see. Tell me what your thought process was for part 1.
G of 2. So we need to find the area between 0 and 2. And it's 2 times 1, 2.
Shade in that area. Okay. So let's see. So we're trying to find the, let's write that down. That's the integral of f between 0 and 2, right? So let's write that down. It's the integral of f between 0 and 2. Perfect. Very good. What's the graphical interpretation of that integral?
It's the area between the curve and the axis.
Good. Which curve?
F of t.
Good. Let's go ahead and label f of t in your picture. Off on the right. Good. Trace out f of t. Trace f of t with your cursor from 0 to 2. Trace it from 0 to 2.
I missed this part.
Okay.
All right. Jeez.
So show me the calculations that you did to find that 3.
2 times 1 is 2. And then you have to add the area of the triangle, which is 1/2 base times height. So 1/2 of 1 is 1/2 times height is 2. So 1. 2 plus 1 is 3.
Let's see. Okay, what was the height of the triangle?
2.
Show where the height starts and where it stops.
Right here and right here.
And how long is that line segment?
1.
Not 2. That's the problem that's been giving us trouble before. Remember we were talking about how it would be better to actually label all the lengths and heights on your picture before you go over and actually try to do the calculation. Because otherwise when we try to do things in our head, it's easy to make mistakes. It would be better to put in a little number there to indicate how long that line segment actually is. because otherwise the only number you see in front of you is a 2, so it's easy to accidentally misuse it. It's also better to write down your calculations a little bit more, because that makes it easier to check them. If you write down that you multiplied 1/2 times 2 times 1, that makes it easier to see when you made a mistake. Okay, so I think now we have that right. Okay, but in future, like I was saying, it's a good idea to actually write out the calculation a little bit more, because if you've written down the calculation, it's easier to check it. It's easier to check something that's on paper than in your head.
Okay. Okay. So.
Okay, that's good. In this case, why don't you write it like a mixed number so we can compare it to your other answers more easily? Okay, good.
Okay.
Let's see. Okay, all right, now we have correct answers. Okay, so this problem gave us some trouble. We made some careless mistakes. We also had some conceptual issues here, though, too. For a while here, we were forgetting that the areas, some of the areas could be negative. That's a very important issue here. So this would obviously be a good question to go back and try again to make sure that we're comfortable with the conceptual issues, and also just how to get through this without making careless mistakes. I think you mentioned on your last test that you started running out of time at the end, so this would also be a good problem to practice, so you can practice how to get these right without mistakes, but also without taking too long, because that's something you'll need for the next test as well. Okay, good. So I think I'll go back to my screen then. All right, I just want to show you. So this is a problem we took from your instructor's website, right? I wanted to show you your instructor built a trick into this problem. You might not have noticed, but on the website, your instructor drew in all these little hash marks. So notice how the hash marks make a bunch of squares, right? How wide is each of these squares?
1.
And how high is each square?
1.
So what's the area of each square?
1.
And how about if we take half a square then? If the area of the square is 1, what's the area of half the square?
1/2.
That's right. So your instructor built in this trick into the problem. For example, the first question was this, to figure out the area from here to here. Well, how big is this triangle?
1/2.
Yeah, and this?
1.
And this?
1.
And this? Oops,
1/2.
I didn't really draw that correctly.
So 3.
So your instructor built in a trick so we can do this faster, basically. So that comes out to be 3, and then they had so then from 6 to 8 would go from here to here. So how big is this triangle?
1/2.
But it would be negative because it's down below. And how about this?
1/2.
So the total area is
0.
That's right. So then this area would be from here to here. So what's this area?
Negative 1/2.
And this one?
Negative 1.
And this one?
Negative 1.
And we already said this one had an area of?
Negative 3.
This little triangle?
Negative 1/2.
That's right. So the total area is negative 3. Good. And now if we're going to add them all up, it would be 1/2 plus 1 plus what?
1/2 plus 1 plus 1 plus 1/2. It's 3.
So let's keep going. How would we figure out the whole area? 1/2 plus 1 plus 1 plus 1/2.
Minus 1/2, minus 1, minus 1, minus 1/2, plus 1/2.
Right. Well, you can actually notice that these two areas cancel. 1/2, 1, 1, and 1/2. That cancels with 1/2, 1, 1, and 1/2, and all you have left is this 1/2. That's kind of the way you did it. So then we get this answer. So that's just kind of a little trick that your instructor built in to make this a little bit faster if it's taking us too long to do these. I didn't actually notice that trick myself until I looked at your instructor's own solutions for that. The reason I didn't point that out to you is that we can't take it for granted that you'll be able to do it that way on the test, right? On the test, you can't take it for granted they're going to set everything up to have either an area of 1 or 1/2. So I thought it was important for us to practice the more geometrical method. The problem from the sample test, I don't think you can do the problem from the sample test like this. So you can't trust that you can always use this method. So I thought it was important practice to do it the long way. But it is interesting to see that your instructor set this up so there is a kind of a shortcut on this problem. Okay, good. Now what we got here was that on this region, f prime was positive. So G was increasing. And in this region, f prime is negative. So G is decreasing. And on this region, f prime is positive. So increasing. And in fact, we could go even further. At this point, f is 0, and G has a local max. And at this point, f is 0. And G has a local min. So where f is 0, that gives you the candidates for where G could be a local max or min. It doesn't guarantee that there's a local max or min, but it gives us the candidates. And remember, what's our definition of G here? G of x equals what?
G of x equals the integral limits of 0 to x of f of t with respect to t.
Very good. That's right. So G is the integral. Do you see how we could kind of say as a shorthand, G is the integral of f?
Yep.
Right. G is the integral of f, because G here is this integral of f as a kind of a shorthand. Now, did all these patterns here remind you of anything? All these little patterns we did here should have reminded you of what we were doing in the previous chapter. Oh, why did I put these primes here? That's totally wrong. I think I started getting confused. Let's go back and get this right. All right, where f is positive, G is increasing. Where f is negative, G is decreasing. Where f is positive, G is increasing. Okay, so now I think I have that correct. So this should have reminded us of the patterns we saw in the earlier chapter. Notice whenever f is increasing, whenever f is positive, G is increasing. Mm-hmm. Wherever f is negative, G is decreasing. And when f is 0, G has a local max. What should that remind you of? Doesn't it seem like f is acting a lot like the derivative of G?
Right.
It seems like f is playing the same exact role here that G prime would have played in the earlier chapter, right? Because we saw that when the derivative of G is positive, G would be increasing. When the derivative of G is negative, G would be decreasing. And where G prime is 0, that's the candidate for G to have a local min or max. So we haven't proved this here, but you should start to be guessing here that f is the derivative of G. F is the derivative of G because it matches up with our patterns that we've seen so far. In fact, when you look at it that way, doesn't this mean that we've really been kind of using the first derivative test for finding the local mins and maxes, right? Where when f changed from positive to negative, that was a local max. Well, that would make sense if G prime was changing from positive to negative, because we know that that's where G has to have a local max. And where f changed from negative to positive, that's where G had a local min. Well, that would make sense if f really meant G prime, because we know that when G prime passes from negative to positive, the first derivative test tells us a local min. So what we've kind of done here is kind of suggested or indicated or proved or illustrated or just suggested that f equals G prime. So how would you read this equation in words?
F equals the first derivative of G.
F is the derivative of G. But what's another way that we've learned in the last few sections to write a sentence like this? If we say f is the derivative of G, what's another way to phrase that in words that we've learned in the last few sections?
G is the antiderivative of f.
G is the antiderivative of f. Good. Now, maybe we should say a antiderivative, right? Because remember, there's many antiderivatives. They all differ by a constant. But at least we can say G is a antiderivative of f. But G is the integral of f. G is the integral of f. And here we're saying G is an antiderivative of f. So that means what are integrals? What I'm saying here is this suggests integrals are antiderivatives. You see what I'm getting at here? If we accept this logic, this makes it seem like integrals are antiderivatives. If G is the integral of f and G is also an antiderivative of f, that means integrals are antiderivatives. Does that make any sense? All right, so that's how this section ties into all the stuff we were doing earlier. It might have seemed like so far in this chapter we've done two completely different things. So we spent a bunch of sessions doing antiderivatives, right? We spent a bunch of sessions doing antiderivatives, and then we spent a session or two calculating areas under curves. We spent some of our time on antiderivatives and some of our time on areas under curves. So you might have been wondering, what the heck do those two things have to do with each other? Well, it turns out that amazingly, surprisingly, you wouldn't have predicted this, but amazingly, you can use antiderivatives to figure out areas. You can use antiderivatives to figure out areas. How do you figure out the area under this curve? Well, you can take the antiderivative of f, and you can use that to find the area. You can use antiderivatives to find areas. That means you can use antiderivatives to find definite integrals, because definite integrals are areas. We haven't proven that, but these patterns that we've been seeing here are very suggestive, that it should help us to accept the idea that the area under the curve, this area so far function really does seem to be acting like an antiderivative. That's the point. this area so far function really does seem to be acting like an antiderivative. Now, why is that important? Well, how did you figure out these areas? You figured out these areas by using the area of a triangle and a rectangle, right? Mm-hmm. But what if I had drawn the function like this?
Right. It would be
impossible to use high school geometry for this because these are not rectangles or triangles, right? How could you find, say, this area? You can't, this is not a rectangle or a triangle. Maybe it looks a little bit like a semicircle, but let's assume it's not just a pure circle. So all you learn in high school is how to find areas of circles and rectangles and triangles, but you don't learn how to find irregular areas like this. How can we find an irregular, or maybe, let me just make it simpler so that the point comes through similar. Here's the formula for x squared. This is the graph of x squared. Well, how would you find the area under the x squared graph? It's not a rectangle, it's not a triangle. How can you figure it out? None of the methods we use today would help us. But now we have a trick because we've just discovered that areas can be found using antiderivatives. Areas are antiderivatives. Now, I'm not saying that's obvious. Like I say, it's almost an amazing fact that antiderivatives can be used to find areas. We're not really showing why that makes sense or why it's obvious or why it's intuitive, but we have kind of suggested that it's probably true from the patterns that we saw here. That we saw here that this curve really did seem to be functioning as if it was the derivative of the area. F really was acting like it was the derivative of the area, but that means the area is the antiderivative of the curve. So what we're going to do next is, it turns out, how do you find this type of integral? So this would be, say, this would be the integral between 0 and 2 of x squared.
Yeah, I think this is what I was thinking of earlier.
Yeah, you might have been thinking about this earlier, except what you were thinking about earlier was the long, hard way to do this. The long, hard way to do this is to use limits. But actually, what your instructor covered first is a shortcut. It turns out there's a shortcut for doing this, and the shortcut is, we just saw, areas are antiderivatives. All we have to do then is take the antiderivative of x squared, and we'll be able to use that to find this area. So we won't have time to go through that today. I'm just giving you a peek into how this ties in to what we're going to go over next. But I thought it was important to see what the relevance of all this was and why it's in the same chapter as antiderivatives. So if someone asks you for this, they're asking for the area under the x squared curve. Well, you can't use high school geometry for that because this is not a triangle or a rectangle or a circle. But now we've got a trick. We've just learned that integrals are antiderivatives. So if we just took the antiderivative of x squared, we could use that to figure out this area. There's a couple of details we'll have to go over, but that's the basic trick that we're going to be seeing. Okay, so I just wanted to try at the end of today to try to see a sneak peek of what we're going to go over next time so we can see what the relevance of all this is. So the questions we did today showed us that this curve is acting a lot like the derivative of the area function. The curve is like the derivative of the area function, but that means that the area is the antiderivative of the curve. Areas are antiderivatives, but definite integrals are areas. So that means that integrals are antiderivatives. So how do you calculate definite integrals? It looks like the way to do that is by using antiderivatives. That's part of what's called the Fundamental Theorem of Calculus. The Fundamental Theorem of Calculus, or maybe part 2 of the Fundamental Theorem of Calculus, says that you can calculate areas by using antiderivatives. You can calculate areas by using antiderivatives, or what that means is you can calculate definite integrals by finding antiderivatives. So that'll be the kind of next thing that we're going to go on to next. Okay, so these last ideas that we're talking about here, I think these are some of the most subtle ideas in the course, all these connections. This might be a good thing to kind of sit and meditate on a little bit, what we did with this chain of logic to see that g is really an antiderivative of f, which means that, I'll write it down this way. That means, remember, what does g represent? G is an area. So areas are antiderivatives. And remember that definite integrals are areas. So we could also say definite integrals are antiderivatives. That's certainly not obvious, but we've kind of suggested that it's true here. this is kind of part 2 of the fundamental theorem of calculus. Areas are antiderivatives, or at least you can use antiderivatives to calculate definite integrals. You can use antiderivatives to calculate definite integrals. Okay, well, we'll have to leave that here, and then hopefully tomorrow we'll get into how we can use antiderivatives to calculate these types of areas. Okay, so as usual, it would be good to carefully review the material we just went through. Remember, your goal is to get to the point where you can get these right in a reasonable amount of time without careless mistakes, so that you don't have to spend too much time on them on the test. We're definitely going to be building on this material tomorrow, so it's important to try to get to the point where you're really comfortable with this material today, so that we can move forward and try to build on top of that. And again, we're going to build a little bit on this chain of logic, so you might want to try to review this chain of logic again in your head. It seems from these patterns that f is like the derivative of g, but that means g is the antiderivative of f, and that means that areas are antiderivatives. That would be a good thing to kind of meditate on for maybe 5 or 10 minutes, because these are pretty subtle ideas, but that's what we're going to try to build on tomorrow. So this is a good time to pause so that you can kind of sit and, like I say, really kind of think and meditate on a chain of logic, because I think it's a pretty hard chain of logic.